Hello everyone, my name is Richard Goldman and welcome to Deep Learning in 15 Minutes. Today we're going to be talking about deep learning basics and help you build your first neural network. So let's dive in. What is deep learning? Deep learning is basically a subset of the machine learning bubble, and in the greater bubble it's another subset of the AI, artificial intelligence bubble. So it kind of lies as a subset of that machine learning realm. Basically, it consists of artificial neural networks. When we're referring to deep learning, we're usually talking about artificial neural networks. And it is used in general to build complex nonlinear models and start learning patterns that are very intricate and complicated. And it relies on big data sets. So it's come into popularity recently because of the revolution in big data and more or less enablement by innovations in computing. Basically, the GPU, the innovations with GPU computing have enabled large data sets and large amounts of computations to be done much more quickly than on CPU chips. And this has actually enabled neural networks to become infinitely more useful. So let's keep on going. Let's dive into it. The basics. What are the basics of neural network? Perceptron. Perceptron is one of the building blocks of a neural network, and it's the simplest neural network architecture. I am showing you the structure initially just because I want you to see how it looks. You're feeding in some input values. You're taking away some of those inputs and maybe adding a bias or a constant term. So it's kind of a linear combination. And then you're adding some activation function. In this case, it's a step function. So if the input meets some threshold, it's 1. If it doesn't, it's 0, and you're getting an output. And that is a perceptron. So let's go into some characteristics of this model. Basically, it's the simplest neural network architecture, but it only works on linearly separable data. So if you look at the right, the purple circles and the green X's, they are linearly separable. But if you had something like at the bottom with nonlinear pattern like that, the perceptron couldn't handle that. Or in the second graph right here, the XOR function, XOR gate, you see there's 2 lines there. Perceptron cannot handle that as well. So what can it handle? It's used to model logical operator gates such as OR, AND, NAND, NOR. So that's pretty useful, but unfortunately, because of the linearity, it can't distinguish the exclusive OR function. So the takeaway here is not that perceptron is particularly useful on its own, but it's important to understand that it forms the building block for much more complex neural networks. And it turns out that if we start stacking perceptrons, we can actually start building these neural networks that recognize these very complex nonlinear patterns. So at the moment, the thing to also note is that perceptron in itself isn't any better than linear regression, and so by itself, you might as well not even waste your time and go just do some linear regression or something very simple like that instead of using perceptron. But this is important to understand so that you can actually start building nonlinear models from this linear model here at the moment. So we can see this nonlinear graph at the bottom right. Neural networks can solve this. So let's go from linear to nonlinear. Let's dive into it. Multi-layer perceptrons. That's kind of the term for what I was talking about when I say stack perceptrons. Turns out if you put them into multiple layers, you can actually start building very complex nonlinear models. And let's actually use the most simple example of this is combining the different logic gates, linearly separable logic gates to make the exclusive OR logic gate. And if you look at this perceptron, we have now added an extra layer, which we call a hidden layer in neural networks. It's this layer in blue. And we feed in our inputs, and we take the NAND and OR function, combine those into a weighted sum, and then we take that output and apply the AND logic gate. And that will give us the exclusive OR. I'm just proving it out, again, in a form of a logic table. And you can see that the AND function applied to the NAND and OR function outputs the exclusive OR function, where the logic gate only outputs 1 when it's either 1 and 0 or 0 and 1, but not both zeros and not both 1s. And you can see how we now have this multilinear division right here on the left-hand side graph. So this leads us into our discussion about neural networks. This application of a multilayer perceptron is a basic neural network at its core. And we're going to see how this translates into our most simple type of neural network, which we call a feed-forward neural network architecture. So feed-forward neural networks, the basics. Basically, just like we had above, I'm going to go into some more detail, and there's a couple of extra nuances that we have to take into account. Basically, starting from the left, we have our input. We apply weights and biases to those inputs and take a weighted sum of those weights and biases. Then we apply that. Then we feed that weighted sum into an activation function. In this case, in the Perceptron's case, we were using a step function, but in actuality, we're going to have to start using a sigmoid, and I'll get back to that in 1 second. Then we take our activation function, apply new weights and biases to that, and take another weighted sum of it. And then we take the activation function of that weighted sum and output as an output. The output is then subtracted or compared to the desired or targeted term to get what we call a measure of error or some sort of loss function. And that's what we have as defined as J over here. It is in this case, we're using a quadratic loss function or mean squared error function. But you can use plenty of other ways to measure error. So let's dive back really quickly. This activation function that we were talking about, this is actually the core of the nonlinearity of the model. If we just use a linear activation function, such as a straight line, or we didn't apply it at all, and we just had those weighted sums, then we would just be stacking linear models on top of each other and end up with a linear solution that would be no better than a linear regression. So this is actually the key of the nonlinearity, is having this nonlinear mapping in the form of an activation function in your across your neural network. And another thing we brought up is why use a sigmoid? Why not just stick with the trusty step function? And that is because the step function is not differentiable. And it turns out that neural networks are just solving an optimization problem. So when you optimize, you need to start calculating derivatives. And it turns out when you need to calculate derivatives on that step function, it gets impossible or very tricky. And so the sigmoid allows us to do that, and it also closely resembles the step function. So it's a very handy in its function, and it's generally kind of the basic bread and butter of neural networks. It's one of the simplest, one of the most common ones that you'll see, even though it might not be the best, but it's generally the things that people start out with. So if you want to pause the video, you can look at how I've defined all of these parts of the neural network. You can kind of look at this structure and see how everything is defined. But I'm going to move forward and basically just say, okay, this is an example of the feed-forward neural network where we're feeding the info forward. As you can see from left to right, it's going forward and to produce input to output. And the next part of this is basically getting to, okay, now that we can feed it an input and get an output and understand kind of how it's getting that output to some extent, we need to actually make it better. So we get an output, we get some error, but we don't have a way of training that right now. And so that's the next question. How does it learn, or how does it get better? And that brings us to our next point. We actually use a concept called backpropagation to help the neural network learn and fine-tune the model. Backpropagation is basically learning and training the model by propagating the error backwards from the error function, starting from the error function all the way back to the input. And we adjust our inputs, our weights and biases based on using this backpropagation technique. And okay, so the next part of this is basically saying, okay, in order to backpropagate that error, we need to know how to make adjustments in our weights and biases to minimize the error associated with that input. So we need some sort of function of J being the loss function or the error function, with respect to the change in weights and biases, aka a derivative. And here's where we come to our optimization problem. More generally, we are solving an optimization problem where the goal is to minimize the loss function with respect to the weights. How do we do this? We use a technique called gradient descent. So we're going to calculate the gradient and descend down the loss function to get to a point of global or at least local minima, and minimize our loss, our error, with respect to the weights and biases and inputs that we gave the model. And we use this handy formula in purple, equation 1, where the new weight, the weight prime, is equal to the old weight minus, and we take minus because we're taking the negative gradient because we wanted to descend down the curve. If you look here on the left, we want to descend, times a learning rate. This alpha term is a learning rate where it's basically just, okay, if we have a gradient, it'll tell us how big of a step to take in that direction. And generally, we want to take the right size step, because if we take a too big of a step, we'll overshoot and maybe cross over to miss the minimum altogether. Or if we take a too small of a step size, we can end up just taking forever to get to that minima. So we will basically be having some sort of step size that's arbitrary, as most things, a lot of these hyperparameters tend to be. So we have a learning rate times the gradient times the input value. And if you want to know more about gradient descent, it's a very key part of this neural networks, but I won't be talking about it in this video. I'm going to go into more detail in another separate video on gradient descent and optimizations for that technique. So how do we derive the gradient? And how do we propagate that error backwards using this gradient? Well, it turns out we need a thing in calculus. We have to start from the loss function, and we need to get the loss function in terms of the weights. But we don't have that defined explicitly. The loss function's over here, and the weights are here and here. And so, we need to actually link those together using a concept in calculus known as the chain rule. And the chain rule basically just says that, if you have implicitly implied functions that are defined within a certain function, then you take the derivative on the outside, then you take the derivative of the inside, and so on. And so we're basically just continuously differentiating the implicit functions within those functions. And you can see here, as we start from the back, delta j with to get to delta j as a function of delta omega, the weights, we can take these differentials in the interim steps to get there. And that's exactly what we've done. And if you follow along in red, it's basically just what I have in black down here, but in the reverse. And you can see how that's why we call it backpropagation, because we start from the back, and we can easily calculate these derivatives as we have the one before it. We can use the one before it to calculate the one after it, and move to the left of the network and adjust the weights based on these gradients here. So the bottom line is we can use the chain rule to calculate gradients where necessary to adjust the weights and biases. Okay, so kind of to sum it up, I want to follow up and talk about the general algorithm for building and deploying a neural network. Basically, step number one is initialize your weights and biases. You're going to choose whether random or whether you have some strategy in mind. You're going to just initialize and set some values to the weights and biases. Then you're going to run each sample through, and for each training sample, you're going to run it through the network, get an output, calculate error from that output, then use backpropagation and gradient descent to step backwards to the network and adjust each weight and bias based on the gradient descent formula that we've defined above and right here in black. Then you're going to, once you've gone through all samples, generally you're going to need thousands of samples. Many sets have 50 to 60K. Then you're going to repeat that for a number of iterations so that you can, get that error down. And you're going to need a decent number of iterations generally. So you can see how, kind of just a quick comment too, if you have 60K samples and you're doing 60K times, let's say 100 iterations, that's 6 million iterations. And, it can get pretty quickly, the computation, it's very computationally expensive to run neural networks. And so that's what we're gonna get into later of, this initial approach may be a little bit slow, but there's many ways to optimize and speed up the calculations and the computation learning rate of your neural network. And I will make a separate video on optimizations, but for now, you're all done. You basically know how to build and deploy your first basic neural network, and you can get it up and running and learning in no time. And look forward to seeing you on my other videos about optimization and gradient descent. Thanks everyone for watching.